Today we're covering section 5.5 on solving exponential equations and logarithmic equations. So as a reminder, we have these log rules where the log of a times b is the log of a plus the log of b. We also have a quotient rule for the log of a over b and a power rule for the log of a to a power p. They correspond to our exponent rules. We'll want to be able to go back and forth between these two and have all 6 of these in mind throughout today's lecture. So equations with variables in the exponents, such as what we have here, 3 to the x equals 20 or 2 to the 5x equals 64, well, those are called exponential equations. In general, if we have two numbers whose exponents match, then those two numbers must match. So if I have some a to the x equals a to the y, my bases are the same there, then that must mean that x equals y. And we will use that fact over and over again. So here's one of the simplest examples we'll come across today. See, we have 2 to the 3x minus 7, and we know that equals 32. Well, for what x value does it equal 32? Well, it's helpful to note that 2 to the 5 equals 32. So 32 equals 2 to the 5. So that means 2 to the 3x minus 7 equals 2 to the 5. Well, that's pretty convenient because now we can just say, well, 3x minus 7 must equal 5. We didn't have to do logs. We didn't have to do any extra work. The bases match, so we just set their exponents equal to each other. If I now add 7 to the other side, I have 3x equals 12. And so that gives me x equals 4. And if I plug that back in, I get 2 to the 3 times 4, which is 12, minus 7 is 5. So I get 2 to the 5, which is in fact 32. Now moving on to with this next one, I have 4 to the x squared times 2 to the 3x, and that equals 4. Now these are close to all having the same base, but 4 is really a power of 2. So let's see if we can write this so that they all have the exact same base. Well, 4 being 2 to the 2 means we're doing 2 to the 2 to the x squared times 2 to the 3x, which equals 2 to the 2, right? If I write 4 as 2 squared, that's totally fine. That means I have 2 to the 2x squared times 2 to the 3x, and that equals 2 squared. Now I can use my exponent rules and add the two exponents on the left-hand side. I have 2 to the 2x squared plus 3x. And that equals 2 squared. Well, now I have the same base on both sides, so I can just set their exponents equal to each other. 2x squared plus 3x equals 2. And now the natural way to solve for this is 2x squared plus 3x minus 2 equals 0. I subtract 2 to that left-hand side, and now I have a quadratic equal to 0 that we solve all the time. So 2x squared plus 3x minus 2, let's see if we can't factor that one. It would be a 2x and an x. And if I have a 2 in my outer position, a plus 2, I think that would work. So if I have a plus 2 and a minus 1, then I get plus 4x minus 1x, which gives me a plus 3x in the middle. So that factoring works. We've done factoring a ton. We have a ton of practice with this. So, if you have any questions on that, reach out. But this does look properly factored. So now we just set each one equal to 0. 2x minus 1 equals 0. X plus 2 equals 0. With this first one, we get x equals 1/2. And with the second one, x equals -2. And there we have solved it. We also have a similar property for logarithms, where if I have the two logs with the same base, so log base a of m equals log base a of n, that means that m must equal n. There is no other option, essentially. So that's helpful. We'll mostly use that we might take the log of both sides of an equation or raise both sides of an equation to an exponent. We might also just set the two, m and n inside parentheses equal to each other. We have different options for using this rule, but you'll see it come up several times. So solving something like 3 to the x equals 20. We want to solve for x. We need to get x out of that exponent. Anytime you have to solve for something in an exponent, you have to take the log of both sides. All right. We'll be able to use that first log rule on powers to move the x to a coefficient and get it out of the exponent. We have to take the log of both sides. Now, that previous slide that said that the log base a of m equals log base a of n, if and only if m equals n, that tells me I can take the log of both sides of an equation without changing the equation. So essentially I can say, well, let's do log of 3 to the x, and that's still going to equal log of 20. Now, these two don't match in base, so there's no rewriting 20 as a power of 3. That's not really going to work here. So we have to take the log here. We can't just set exponents equal to each other. Sometimes that works out in certain examples like we saw at the beginning, but not always. So we take the log of both sides, and here's where we're at. It's totally fine to go with base 10 here. I would suggest if there's e's in the equation to do a natural log. Those are pretty much the two that you'll deal with, log base 10 or natural log. Here, log base 10 makes sense. What we can do now is move that x out of the exponent and put it in the very front. So then we get x log of 3 equals log of 20. That's using our power rule. Now to get x alone, I'm one step away. I just have to divide by log of 3 on both sides. Well, that's just going to be x equals log of 20 divided by log of 3. And we can use our change of base rule to bring this to log base 3 of 20. We covered that during our last lecture. I believe it is okay on Pearson to leave it as log of 20 over log of 3 here. So that is our problem. That is our, solution to our problem. And I apologize if you can hear my cat crying in the background. She's just trying to say hello. All right, moving on. Here's our next problem. Again, our bases don't really match, and we have x's in the exponent that we need to solve for. So let's take the log of both sides. Log 4 to the x plus 3 equals log 3 to the minus x. Then we can take our x out of the exponent and move it to the front. So we get x plus 3 log of 4 equals negative x log of 3. Could really just x times. There we go. So now let's get all of our x terms on one side, non-x's on the other. Basically treat log of 4 and log of 3 as numbers. They're just kind of coefficients that hang around. They don't do too much at this point. We're just going to use some algebra on the x's to get them alone. So let's break up those parentheses on the left-hand side. We would have x log of 4 plus 3 log of 4. All I've done here really is taken this log of 4 and distributed it to both terms. And we're not going to change the right-hand side. So now our goal is to have all x terms on one side, non-x's on the other. So I'm actually going to subtract my x log of 4 to the right-hand side. And we have 3 log of 4 equals negative x log of 3 minus x log of 4. I've subtracted that x log of 4 to the right-hand side. Well, now I can factor out an x on the right-hand side. So 3 log of 4 doesn't change. And I can take an x out, and I have minus log of 3 minus log of 4. Well, that's great because now we're just one step away. We get 3 log of 4 divided by negative log of 3 minus log of 4 equals x. We did that last division step, and that's it. Now that's something you could plug into your calculator to simplify if you needed to. But here we have the exact simplified answer for x. Now let's see an example with e in it. When we see an example with e, I highly recommend using natural logs. Let's do one step first. I'd love it if e was alone. It would make our lives a little bit easier. So I'm going to divide that 100 from the left-hand side to the right-hand side. So let's say divided by 100. Then I have e to the 0.08t equals 2,500 divided by 100 is just 25. So that's already a little bit simpler. But now we're solving for something in the exponent. So we need to take the log of both sides. Here we're dealing with e, so I think it makes sense to use a natural log. If we use a natural log, ln of e to the 0.08t equals ln of 25. Now we haven't changed the problem just because we took the natural log of both sides. So it's totally okay to do that. Now the e and the natural log, well, they're inverses. They cancel each other out. So we have 0.08t equals natural log of 25. That means t equals natural log of 25 divided by 0.08. Again, something you can just plug right into your calculator. This is, of course, going to be a decimal, but that's quite all right. Let's see another example. Here we have t in the exponents, but it's on both sides. So we'll go ahead and use our natural log here since we have an e and see what happens. So let's take the natural log of both sides, e to the minus t equals natural log of 9 to the 5t. Our e and our natural log cancel on this side, and we just have minus t. Now on the right-hand side, we're going to use our power rule and bring the 5t to the front. So it looks like that. That's what our power rule allows us to do. Now we have an equation with t's on both sides, and we can't have that. We need all of our t's on one side so that we can solve for it. So I'm going to take the t from the left-hand side and add it to the right-hand side. We get 0 equals 5t ln of 9 plus t, just like this. Now we have two terms with t's in them. Whenever we're solving like this, we factor a t to the front. 5 ln of 9, the t is gone, plus 1. And this equals 0. And so we're actually going to divide by 5 ln of 9 plus 1 on both sides. But look what happens. We actually just get t equals 0. And that's okay. Just the algebra showed us the only place where these two things are equal, well, that's when our t equals 0, which of course anything to the 0 power is 1. So that makes a ton of sense here. Now we also have what are called logarithmic equations. So if we have expressions containing variables inside of our logarithmic expressions, that's what we call a logarithmic equation. The way to get rid of these is to always combine logarithms into a single expression, and then we're going to have to write the equivalent exponential equation. So let's see what that looks like. Here we have log base 3 of x equals -2. The way I like to think about this is, well, what if we considered 3 to the log base 3 of x and 3 to the -2? That earlier rule said it was okay to do this. And there's no great phrasing for this that I've found. I've really just raised 3 to the both sides, essentially. So now the 3 and the log base 3 cancel, and I get x equals 3 to the -2. And that's it. Now, really with this one, it's so simple. We could have just immediately applied our log rule, where by definition, we know 3 is our base, -2 is our exponent, and x is what it equals. That also would have given it to us, but not every question is going to work out quite that nicely. It kind of just depends. So now we have log base 2 of 10 plus 7x equals 7. Again, let's take 2 to the both sides. So 2 to the log 2 of 10 plus 7x equals 2 to the 7. Those cancel, and so we have 10 plus 7x equals 2 to the 7. Again, kind of comes out of the definition of this one. Lastly, we just got to solve for x. So we take 7x equals 2 to the 7 minus 10. And we divide by 7, we get x equals 2 to the 7 minus 10 divided by 7. And that's it for this problem. So we have another one. Now we have multiple logs going on. So we actually want to combine these logs first. That would tell us, using our product rule, that this is equal to log of x times x plus 3. And this equals 1. So I haven't taken any logs here. I just used our log property. Log of x plus 3. Now this is a log base 10 question, so we could think of this as 10 to the 1 equals x times x plus 3. There are a few different ways to get here, but this is the equivalent exponential expression, right? I know my log base is 10, and I know my exponent is 1, since that's what the log equals. And so 10 to the 1 must equal x times x plus 3. We can simplify this more. The right-hand side becomes x squared plus 3x. And if I subtract the 10 over, we end up here. So now it's quite easy to solve, or at least at this point in the course, I hope it is. We can just factor, and then we're pretty much there. Let's see, x plus 5, x minus 2 gets the job done. So then we have a plus 5x minus 2x in the middle. So that works out well. And if we set each one of these equal to 0, we get x equals -5 and x equals 2. Now, we can actually check our work here, right? So the original question was log of x plus log of x plus 3 equals 1. So log of x plus log of x plus 3, does that equal 1? Well, log of 2 plus log of 2 plus 3, does it equal 1? Let's see. Let's go to our calculator and find out. There's the calculator. Here we go. So log of 2 plus log of 2 plus 3. And yes, we got 1. Now we can check it similarly for our x equals -5 and look at log of -5 plus log of x -5 plus 3. Only this one actually doesn't work. This one actually is not in our domain because we can't take the log of a negative number. So actually, x equals -5, not correct. We actually only want to take x equal to 2. Again, we cannot take x equals -5. We cannot take the log of -5. Therefore, our only answer here is x equals 2. So you have to throw out certain x values sometimes. You have to make sure that x value is actually in your domain. On to our next example. This one's just a little bit different from what we had before. See, we have log base 2 of x squared minus, now I am going to drop that 3 to the front, 3 log base 2 of x minus 10, moving the 10 to the other side, this equals 0. Well, isn't that interesting? This is something where I have something squared minus 3 times the same thing minus 10. Does this remind you maybe of something that actually factors? So if for a moment, let's take u and do a little substitution. Log base 2 of x. That means we have u squared minus 3u minus 10. Well, that's something we can definitely factor. That becomes u minus 5, u plus 2. Therefore, we get u equals 5 and u equals negative 2. So we can actually take our log and plug it back in for u. Essentially, we put u equals log base 2 of x. So now we have log base 2 of x equals 5. And log base 2 of x equals negative 2. Therefore, this corresponds to base 2 exponent 5 equals x. Base 2 exponent negative 2 equals x. So those are our two x values. That's a minus 2 up there. And it really did come down to just recognizing the shape of the problem, using one little power rule, and then actually just doing kind of some factoring and substitution back in. So a little bit tricky here, a little bit tricky to recognize, but we can't actually use any other rules on that log base 2 of x squared. There was no other way to handle this. So that is how we get our two x values. Now moving on. We have ln of 4x plus 6 minus ln of x plus 3 equals ln of x. So let's use our rules here and see what we can figure out. Essentially, I have ln 4x plus 6 minus ln x plus 3 minus ln of x. This equals 0. Okay, so now I have ln. Now, bear with me. I'm going to do these rules in one step. I have a positive 4x plus 6. And then I have a minus x plus 3 and a minus ln of x. Well, those minuses means we're going to use our quotient rule and put in our denominator. X plus 3 times x. So that means that the natural log of this whole stuff equals 0. Well, rewriting this using our exponents, we know if we have a base e, exponent 0, that this must equal what we have in parentheses, 4x plus 6 over x plus 3 times x. But e to the 0 is 1, which means we need to know when 4x plus 6 over x times x plus 3 equals 1. Well, let's solve that. If I have 4x plus 6 over x times x plus 3. I'm really going to multiply that out. Just go ahead and do this. X squared plus 3x. That'll be helpful. Set this equal to 1, and let's try to solve this guy now. Well, we have a fraction, so I think my first order of business is to get rid of the fraction. We have 4x plus 6 equals x squared plus 3x. See, I can just multiply the x squared plus 3x to the right-hand side. So now let's get all of our terms onto one side. I'm going to subtract 4x and subtract the 6, and I get 0 equals x squared. Now 2x minus 4x is minus 2x minus 6. That is now factorable. Let's see, power or multiples of 6, 2 and 3, or 1 and 6. I don't think that factors quite nicely. Let's go to the graph. I think that's the easiest way to find this one out. I'm trying to find when x squared minus 2x minus 6 equals 0. Y equals x squared minus 2x minus 6. No, so you see how it does not cross the axis very nicely at those points, but we can just calculate those zeros. I go to my left bound, graph, calc, 0, go to my left bound, enter, I go to my right bound, enter, one more time, negative 1.646. I'm going to write that on the slides, x equals negative 1.46. 646, I said. Okay. Now let's calculate the other zeros. So I can calculate 0, and we go to the right. We need do the right 0, but I want to stay to the left of it. I hit enter. I keep going, and I hit enter. Oops. What did I do? Let's do that again. Calculate a 0. I go to my left bound, enter. I go to my right bound, enter. Enter one more time. I get 3.646. Let's go to our slides. X equals 3.646. Now that we have these, looking at these, we know we can throw out this 0. Since it's negative, it's not in our domain. So we just have our other x value. We might have wanted to use the quadratic formula or something on this to perfectly factor it, but decimals are okay for this example. Just ensure on Pearson that you round to whatever they're asking for, whether it's the 100th place or the 1000th place. Just take care of that and take note of that. All right, time for our last example. We have e to the 0.5x minus 7.3 equals 2.08x plus 6.2. We're actually going to solve this using our graphing calculator, and we're going to plot y1 equals e to the 0.5x minus 7.3, and y2 equals 2.08x plus 6.2. With these, then we can just find where they intersect, and we'll be able to find our x value. So back to our calculator, y1, well, that was e to the 0.5x. That's not e. E to the 0.5x minus 7.3. And then for the other one, it is 2.08x plus 6.2. When we graph these, there you have it. Let's zoom out a little bit. Let's go to our table. How far out should I zoom out? You can see they really start to overlap. That really just keeps growing. So let's go to our window, and we're going to go from -10 to 10, maybe to 20. And let's go to my y values. Oops, my y window. I also want to have a max of 20. Let's see what that looks like. We're starting to see an intersection point up there, so let's zoom out a little bit more, and I'm going to change my window from 0 to 30. There we see our intersection point. So let's calculate that intersection point. Intersect. There's the first curve, second curve. I hit enter one more time. I get 6.61. Now notice I didn't pay any attention to that intersection point that was in our negative area, because it doesn't matter when we have a negative x value. So 6.610. Back to our slides, x equals 6.610. And you know what? Let's go ahead and go back for the other intersection point. Our negatives do matter here. We have a function with e, not a function with natural log. So I misspoke just a second ago. We actually do want to find that negative intersection point. Let's go back to our window and zoom back out a little bit. See, on the left there, it's a valid point because, again, we can plug negatives into e. We just cannot plug negatives into logs. So if I go to second calculate, and I want to find that intersection, and I am going to go a bit to the left just to make sure I'm getting the other intersection point. Oops. Second calculate, intersect. That was my bad. Let's keep scrolling. Keep on scrolling. Enter. Second curve, enter. And there's the other intersection point, -6.471. So we go back to our slides now. And we have x equals -6. I believe it was 471. Something like that. So those are our two x values. Again, they're both valid to plug into e. It's no problem. Of course, we can plug them into the line on the right-hand side. And so these are our solutions. And again, it came down to solving for those intersection points. So as always, please reach out if you have any questions.